Hi, here's a question on curve sketching, and you're asked to sketch the graph of a polynomial, and you're asked to indicate all important features. And the polynomial we have the graph is simply y equals 4x cubed minus 3x to the power of 4. And the important features are typically extrema, the high points, low points on the graph, inflection points, the points where concavity changes from up to down, like for example, concave down to concave up, and intercepts. And we've done that in pre-calculus courses, x equals 0, y equals 0. So the first thing we should actually do is to find the first and second derivative, because we'll use those to help sketch the curve. And the derivative of y equals 4x to the power of 3 minus 3x to the power of 4 is simply 12x squared minus 12x cubed. Now I factored it here because we're going to use it later. Then we find the second derivative, and the derivative of 12x squared is 24x, and the derivative of negative 12x cubed is minus 36x squared. Again, taking out a common factor here. Okay. So once we do that, we can go in and actually find important features and find the important points on the graph. And to find extrema, high points, low points, you let the first derivative equal 0, and you solve for x. And those values are critical numbers. So in this case, when I solve for x equals 1, x equals 0. And these are critical numbers. And what we have to do now is test the intervals to see if they're increasing or decreasing. And if there is change in the interval, we can determine whether it's a maximum point or minimum point. And it's really straightforward to do. So what you would do is take a value less than 0, negative 1 for example, and plug it into the first derivative and see what the sign is. Now some textbooks would require you to list that number. I don't. And again, I'm more interested in the sign. So if we take a number and plug it in here, I get a positive number. So every number here, this interval is increasing. Y is increasing. Then you take a number between 0 and 1, say a half. Again, plug it into the first derivative. Check the sign, and it's positive. And likewise, for x equals x greater than 1, you take a number greater than 1, say 2, plug it in, and the interval here is going to be negative. Let's erase this, make it a bit neater. So essentially what we've got by doing this, we know where the graph increases and decreases. So the fact that the signs change here, so it's increasing to 1 and starts to decrease, means I got a maximum point right here. And if the x value is 1, to find the y value, you plug it back into the original equation, not the derivative. So if x equals 1, y equals 1. And that will be the maximum point on the graph. And what I did here is I actually listed the intervals where it was increasing and decreasing. And it's fairly easy to see from the diagram we have. From 1 to plus infinity, here, it's decreasing. And that's the interval which is decreasing. From 1 to minus infinity, it's always increasing. So y is increasing on the interval of negative infinity to 1. Now it's not asked explicitly here, but sometimes it is. If it is, that's all you have to write down as your answer. And you get that from that diagram. And that's the only extreme point here. So the point 1, 1 is an extreme maximum point. So now we're going to use the second derivative, y double prime, to find inflection points. So that the second derivative equals 0, solve for x, and do the exact same process. Now if the signs change from interval to interval, we've got an inflection point. So the concavity changes from down to up or up to down. So again, take a test value from this interval here, plug it in here, see what the sign is. It's minus, so it's concave down. And take a number between 0 and 2/3, plug it into the derivative. It's positive, so it's concave up. So the fact that these two intervals change from negative to positive means I have an inflection point at 0. And if I take a number greater than 2/3, plug it into the second derivative, check the sign, it's minus, so it's concave down. And the fact that the sign changed from plus to minus means I have two inflection points at x equals 0 and x equals 2/3. And again, we know that since the signs change, got inflection points change from concave up to concave down. Let's erase this. And as before, to find the y value, you simply plug x equals 0 into the original equation, and you get y equals 0. You plug 2/3 into the original equation, and you get y is equal to 16 over 27. So the two inflection points, which we know from here, are 0, 0, and 2/3, 16 over 27. So we're done with inflection points. Now then we have to find the intercepts, and again to find the x-intercept of y equals 0. We knew that anyway from here. And to find the y-intercept, x-intercept of y equals 0, solve for x. I factored here, x equals 0, x equals 4 over 3. So we know that 0, 0 is always already the intercept. This is the other x-intercept. Now, quickly, erase this so it's a bit easier to see. And again, the sketch itself is not worth a whole lot. It doesn't have to be a work of art, trust me. You'll see in a second what I mean. And what we do, again, this is a graph off of a graphing utility off the internet. I just cut and snipped it here. But we know that at 1, 1, 1, which is this point right here, we've got a relative maximum point. A relative maximum point. We have an intercept at 0, 0, so we're set. We have an intercept at 4 over 3, comma 0, so we label that. Somewhere between 2/3 and 17, 16 over 27, which is about here somewhere, we've got an inflection point. So that's going to be 2 over 3, 16 over 27. And if you go back to the concavity, we know it's concave down at 0. So what that means is that 0, 0, this graph is concave down. And from 0 to 2/3, it's concave up. And from 2/3 to plus infinity, we know it's going to be concave down, but it has to go through the maximum point here, so it's going to go through this point and the intercept. Looks kind of messy, I know, but you don't have to give solid points. Essentially, find the important values, label them, and sketch the curve. Okay, and that's how we graph a polynomial. I'll do another example soon of rational function. The only difference with that one is we had to find intercepts, both vertical and horizontal if they exist.